So hello guys and welcome to the second lesson. I'm Bitfriends from Dark Army and today I'm going to show you how to call function with modified arguments. And our goal is to execute the system function from libc with the argument -h so that we can get a shell without placing shellcode on the stack. So let's get started. I already programmed the example program to save time. So let's take a look. So we have three functions here. So first the main function, which calls the vol function, and the vol function just has a char array called buff and reads a bit too much characters, up to 160 characters. And it's obviously too much for 16 bytes, and this will cause an overflow if you enter a longer string. And our goal is to call win and modify the argument so that the arg1 is dead beef and the arg2 is dead code. So last time we learned how to call functions normally without any arguments. And today we're going to show you how to change the arguments. So first we compile our program. So I have to admit that the function calling thing is different on 64-bit and 32-bit, because on 32-bit they are stored on the stack and on 64-bit they are stored in registers like RDI or RSI, like that. So first I'm going to show you how to do it in 32-bit. So let's compile our program with GCC and the no stack protector flag like last time, and the no PIE flag so that ASLR for this binary is turned off. And -n32 for that the compiler creates a 32-bit binary and our program. So let's execute our Docker container. So like that. And GDP out. So let's get the offset from this program. Let's create a simple pattern with 4 characters each letter. To get the offset until the saved instruction or the saved EIP on the stack. So I think that's enough, so let's execute this. And we get a segmentation fault at 48484848, and that's actually this is actually H, the character or the letter H. And by the way, on 32-bit you have the advantage that you don't have to look at the stack. Instead you get the address where you crashed or where you can't execute code because it's out of memory. It gets displayed directly here. So so now our offset is this whole text. So last time we did a simple Python inline script, and that was enough because last time we did just simple function call without any arguments. But this time it's more complicated, and I recommend you to use the Python library pwntools. We will import it like this. We can specify our process. Like that, and we can send input to our process with send line. And first we send our pattern. The next step we're going to get the address of the win function, because we want to call the winch function to get here. So this is this address, and let's save it in a variable in Python like that. And now we can send this as little endian. Yeah, Python pwntools has this nice function p32 which returns this address as a string in little endian, and it's quite helpful. And now I'm going to create another pattern. Yeah, you will see later why I do that. But yeah, I'll say you soon. I tell you soon. Like that. So, wait, we can do, or we can call the interactive mode so that we can have an interactive shell, and it's quite useful. And save it x.py. And let's add pause to attach our debugger so that we have time to attach our debugger. So we can execute our Python script, and we're going to open a new tab and attach our debugger there. Okay, we use the -p flag and specify our PID or process ID of our program, a.out. It's easier with this Linux command so that we don't have to look up the PID manually. Yeah, that's a lot easier. Okay, so let's just break at win and continue. And yeah, continue. Okay, we successfully called the function win. Yeah, that's not special. We did that last time. Yeah, but the interesting part follows, because yeah, we're going to compare this EVP plus 0x8 with that beef. So that's our first argument here. And let's see what that value looks like. So that's 42, 42, 42, 42, and that's actually B in ASCII, and that's this string. And the second argument is here on plus 0xc, so 4 bytes further, and this is 43, 43, 43, 43. Sorry, this is C for ASCII. So we notice that we can control the arguments with, wait, let's continue and then we take a look again. So if we continue, we get a segmentation for it, for 1, for 1, for 1, for 1. So if you know that, we can say that this ace is the return address, and the B's are one argument, and the C's is the second argument. So like that, like here red, and here arg1 and arg2. So if you want to call like main again, we have to specify here the address of main, call the win function with those arguments, and yeah, this is just, yeah, we don't need that because yeah, we are actually executed, or we already won because we arrived here. But for complicated ropchains you need the return address to control. But let's solve that challenge. So yeah, we don't need to change the red address because we know we are done if we control the arguments. Yeah, so we need the argument 1, that beef. We type that in little endian, So that's our argument 1. Now our argument 2. Okay, this should work now. We will not exit cleanly, but that's okay. And we can execute this. And we get you win and segmentation fault, but we don't care. So now let's take a look at 64-bit. We're going to compile the program again, but without this -M32 flag. Yeah, and execute Docker again. So now we need to change our exploit again, so I will remove that. So first let's GDB into our program and create a pattern with 8 characters because we are on 64-bit. And yes. Okay, I think that's enough. So we run that. Take a look on the stack pointer. So, and we crashed at this address. So that's hex 44. So 1, 3, 4. So at our Ds. So our offset is this string before. Let's send that. Now our win address, so yeah, we use the p64 function, yeah, to send the hex value as a string and a little endian, just like the 32 function, but yeah, we're on 64-bit. And now we have to get the win address from the win function again, so like that, and yes. And this should be it. So now we can call, or now we call this function with this program. But yes. So let's run the Python script and attach GDB, break at win, and continue. So we arrived at win, so this worked, so we called win. Now you can see it's a bit different because this is compared with our arguments, but before that the value of EDI is moved into that, and then the value of ESI is moved into that one. So if we control these registers, we can control the arguments and win. So here comes something new. We have to use rob gadgets. I will show you those gadgets. So we can get all rob gadgets from our binary with this tool, rob gadget, and we have to use --binary and our program and --rob. So now we get rob gadgets, and we need to control the RDI register and the RSI register. So it would be good if we use a pop instruction, because you know what pop does? It pops the first value from the stack into the following register, so RSI and yes, or RDI, yes. And then a ret instruction is performed, and then the first argument on the stack, so the saved return address, will be popped into EIP. So this is because the argument is popped earlier in RDI, it's no longer on the stack, and then the next address on the stack is the return address. So we could create a rob chain like this, like pop RDI like that, then our string like arg1, and then the return address, so where we want to jump next. And if you want to control RSI, yeah, we use the pop RSI, our then our argument arg2, and then we have to call the win function. So first we prepare the arguments, so the registers with this rope chain, and then we call win. So I hope you understand this. So let's get the addresses of the gadget. So first the pop RDI, and then pop RSI. So this is this one. We have to be careful. After that there's another pop instruction which pops the current value on the stack into R15, but we don't need it register, so we can just enter a garbage value which we don't really need. So let's enter this gadget, pop RSI underscore R15 to our gadget address, and now we can create our first rope chain. So we use pop RDI for the first argument. So let's send it as a string in little endian with this function. Then we specify the argument. So I will just specify a random argument like AAA to show you that it works. Then we use the next gadget, pop RSI with AAA like that, and now we pop the next value, what we're going to type next, into R15. So we use so I will that will be a useless value, so I will type just junk, that will be stored into R15, and then we call our win function. So now we have our arguments prepared. The first argument is AAA. I will change this to BBBB, so that we can identify our arguments. So now this should work. I will run our Python script again. Wrong terminal, so this one. And now we're going to attach with GDB, break it win, and continue. So let's take a look at the registers. Like let's take a look at EGI. This is 414141. So our first argument, and let's take a look at ESI 424242. Yeah, that's also good, and we can take a look at R15, but that's not important. We don't need it registered yet. That's our string junk. As you can see here. And now we have this is moved into the RBP -4 register and compared with that beef. So that's not going to work because we have to specify we have to enter the real argument, so that beef and that code. So I will create two variables, arg1 and arg2, and the first is that beef, and the second is that code. So now we can send that also as a 64-bit string, arg1, copy that, and arg2. Now let's take a look if it works. You win. We control the arguments, and this is pretty cool. So now that you have the knowledge how to call functions and change the arguments, you could theoretically do that by yourself, but I will show you this anyways. So we're going to execute the libc function system with the argument bin_h. So we know where the arguments are stored. The first argument is stored into RDI, the second on RSI, the third on RDX, and on 32-bit, yeah, they are stored on the stack. So, and I'm going to execute bin_h at this 64-bit program, so our arguments are in registers. So I will turn off ASLR, so that's easier. I will first switch into root. Oh, sorry. And now I will turn off ASLR. Okay, now ASLR is turned off. And yes, and now we can run GDB and get the address of the system function. So we just type p and system. We have to run it first, and yes, p system. This looks like this. This is the system function. So change win to system. And this also. And now we have to find bin_h, or we have to pass the argument bin_h. So this is easy because in the libc, in every libc there's a bin_h string, so we can just find that. Let's just look at the memory mappings. And we can use the find command in GDB, and we specify the start address of the libc and the end address and the string we want to search, and we get one result. And I will show you that this address contains bin_h, like that, and this will be our first argument. Yeah, and we need only one argument, so we just need this gadget, the address of the bin_h string, and the system function. So I will create a new ropchain. So first we need to prepare the arguments, so p64 and pop RDI, because the first argument is stored into RDI. Then we need the system, no, we need bin_h, sorry. So the arg1, there's our system bin_h string, and then we have to call system, and this should give us a shell. Yeah, and because if we want to get a shell and use pwntools, we have to use p.interactive so that we can interact with the shell we got. So let's run this Python program and see if it works. Okay, this is a segmentation fault. So let's just see. We will do a pause is already in there. So we will attach GDB. And we disassemble our vuln function, and break the red instruction to take a look at the ropchain. So yes, now we're going to execute this pop RDI and red. So we can use next instruction. Pop RDI is executed, or red is executed, and then we call system. And yes, so we have a segmentation fault at this address. So sometimes it helps if we add a red return instruction, so as a little rock gadget, so we can do that. This is one, and just call this red. This helps sometimes. I hope it does. And red, yes, we have to get it in our option. Yeah, maybe this will work. We will see in a minute. And let's cross our fingers and type ls. And nice, we got a shell. That's awesome. So yes, so we called system like this. I will show you like that. So we called system like that with building a rock chain, and yeah, we can successfully control the arguments. And I will show you next lesson that you can do much more with our rock chain or with the function arguments than you might think. You can leak addresses and defeat ASLR, but that's for the next video or for the next lesson. So yeah, I hope you liked the video, and yeah, let me think. I want to give you an assignment, so I'm going to change the program a little bit. No, wait. Okay, this assignment is hard. Don't get mad if you can't do it, because it's kinda hard, but you can do it with this, what you learned today. So you will get the same code, but you are not allowed to turn off ASLR like me with this root and echo 0 to this. Yeah, so you have to have ASLR on, and you have to somehow get a shell, so the win function is not important. You only need this part, and yeah, it's not that hard, but yeah, don't get mad if you can't do it. So I hope you guys had fun today and learned something, and I hope I'm a good teacher, and yeah, I think I see you guys next lesson. So goodbye.